This is the second part of section 4.1. In this part, we talk about linear dependence and independence of functions. You're going to see this in Math 26 in linear algebra as well. So we start by introducing a definition, a set of functions f1 of x, f2 of x, all the way to f sub n of x is linearly independent on I if there exists, if you like to write it in simple, that means there exist constants, namely c1, c2, all the way to cn, not all 0, such that c1 f1 of x plus c2 f2 of x plus plus cn fn of x equals 0 for all x in the interval I, belongs to the interval I. That's what the definition of linearly independence. So let's say for dependent, what happens? For dependent, just for two functions, say this equal to 0, then we can solve for one of them. Let's say I want to solve for f1 of x by dividing by c1 first, and this is simply a constant, so f1 of x is k times f2 of x, so one of them depends on the other. So that's for linearly dependent. If one function can be written as a multiple of the other function. So for example, let's say we have f1 of x is cosine 2x, f2 of x is 4 minus 8 sine square x. Then how do we check if these are linearly dependent or independent? Well, one thing I know about cosine 2x, the double angle formula for cosine, it's 1 minus 2 sine square x. So if you take this and multiply it by 4, what do you get? 4 minus 8 sine square 2x. And that's really f2 of x. So that shows that f1 of x and f2 of x are linearly dependent. Another example, f1 of x is x and f2 of x is opposite value of x. Now, these two functions are not linearly dependent, not dependent on the entire domain negative infinity to infinity. But if we take x bigger than 0, because opposite value has to do with either positive case or negative case. If it's bigger than 0, then f2 of x can be written simply as just an x. So then if I do c1 f1 of x plus c2 f2 of x, if I set that equal to 0, c1, this is x, c2 is also x, equals to 0, you get c1 plus c2 is 0, so c1 equals negative c2. So they are dependent. Similarly, if you go from negative infinity to 0, you get c1 f1 of x minus c2 or plus c2 f2 of x equals to 0. c1x minus c2x equals 0. So you get 0 equals 0. Those are also dependent. not 0 equals 0. C1 equals C2. They are also dependent because one of them can be written as a product of the other one or a multiple of the other one. Now for linearly independent functions, we have something to introduce here for linearly independent functions. Another way to check for linearly if functions are independent or not, linearly independent. Suppose we have f1 of x, f2 of x family of functions, fn of x have at least n minus 1 derivatives. If the determinant, in this sense, f1 prime, f2 prime, like derivative fn prime, all the way down, f1 to the nth minus 1 derivative, f2 to the nth minus 1 derivative, fn to the n minus 1 derivative. If this does not equal 0 for at least one point in the interval I, then we say that the functions f1 of x, f2 of x, all the way to fn x are linearly independent. So this thing that we just wrote here, we call it Wronskian. The Wronskian, we use notation for that: w of f1 of x, w f of 2 of x, all the way to fn of x. This is just a notation here. So this stuff here, that's called the Wronskian. So what we have here, we can say if f1 of x, f2 of x, all the way fn of x are linearly dependent and have at least n minus 1 derivative in I, then the Wronskian for f1 of x, f2 of x, fn of x is 0 for all x in I. So as an example, let f1 of x be 2, f2 of x be x. If we need to find the Wronskian for this, w, we call it w of 2 comma x, because these are the two functions given, is the determinant. What do we have here? The function is 2 and x. We find, because there's two functions, we go one derivative, one less. Three functions, you can do two derivatives. So it's only one derivative. Derivative of 2 is 0, derivative of this is 1. Now the determinant is you multiply this by this 2, always minus this by this 0. So that gives us 2, which is not 0. Since the Wronskian is not 0, then we can say f1 of x and f2 of x are linearly independent. Linearly independent. By the way, note if the Wronskian of f1 of x, f2 of x, all the way to fn of x is 0 for all x in I, this does not mean or necessarily mean, this does not mean or necessarily mean the functions are linearly dependent. So basically, the converse of what I wrote here, the converse of this is not always true. So this is saying if the functions are linearly dependent and the condition for derivatives is met, then the Wronskian must equal to 0. But if the Wronskian is 0, that does not mean they are linearly dependent. That's not necessarily true, that they are linearly dependent.